안녕하세요. 저는 토론토 대학에서 포닥 과정을 하고 있는 박엘리아입니다. 저희 연구실 Advanced Pharmaceutics and Drug Delivery Lab에서는 어, 제약학을 기반으로 새로운 나노 약물이나 아니면 마이크로 니들 같은 경우를 통해서 약물을 질병에 잘 전달하는 방식을 연구하고 있습니다. 오늘 발표 주제는 알츠하이머병 치료를 위한 BDNF, 뇌유래 신경영양인자 기반 나노약물 뇌 전달 시스템에 관한 것입니다. 본 연구는 Advanced Healthcare Materials에 게재가 되었습니다. 관심이 있으시면 찾아보시길 바랍니다. Alzheimer's disease um, is very challenging disease for treating because it has a multifactorial pathology involved in the disease itself. It includes the toxic accumulation of proteins such as amyloid or tau. There is a dysfunction in neurotransmitters, neuroinflammation, and other vascular dysfunction and synaptic dysfunction, etc. So that all these pathologies, unless they're treated individually, is hard to modify the disease progression with a single targeted therapy. On top of that, there is a difficulty delivering the drugs into the brain because of the existence of blood-brain barrier. Blood-brain barrier is a barrier that protects the brain from the other organs and other systemic circulation so that not any substance can easily enter the blood-brain barrier and the brain. However, while it is protective, it may be difficult to treat the Alzheimer's disease because of this BBB. It is known that 98% of small drugs cannot enter the brain because of the BBB, and less than 0.1% of the protein cannot enter the brain. Therefore, even if you find a cure for the Alzheimer's disease, you may not be able to see the therapeutic benefits because of the low absorption into the brain. BDNF, which is brain-derived neurotrophic factor, is known to be very beneficial for the brain health. Like any exercise activity, such as vigorous or aerobic exercise, or the healthy food, such as the antioxidative food or the fish and fruits, are known to increase the BDNF, therefore helpful for preventing or treating the Alzheimer's disease. You might have heard of it from the health-related news that fasting or the exercise or any health-related activity that's known to promote the brain is likely to be linked to BDNF. For example, exercise can increase the BDNF level as well as its receptor. So why is BDNF so important in the brain health and then Alzheimer's disease? This BDNF is known to increase the survival of the neurons as well as their connection, which is contributing to the memory. That's why BDNF play critical role in the Alzheimer's disease treatment. However, BDNF has a very short half-life of less than 3 hours. And then when you just administer into the intravenous, a very small portion of BDNF can enter the brain. Therefore, it needs to be administered directly into the brain. And it's in terms of financial aspect, it is quite pricey protein to synthesize. That's why even though we know that BDNF is very beneficial, there's low translational aspect because of these poor pharmacokinetic properties. Our lab specializes in polymer lipid nanoparticles, and we have developed brain-penetrating polymer lipid nanoparticles. These nanoparticles contains polymer and lipid onto its component so that it takes the benefits of polymeric nanoparticle as well as the benefit of lipid nanoparticles. These polymer lipid nanoparticles consist of polymer, lipid, and the BDNF, which is a drug, and is also decorated with the anti-amyloid beta antibody so that it can go to the disease region once it entered the brain. This polymer consists of a starch backbone that is conjugated to polymethacrylic acid, which has pH responsiveness, so it's known to be more activating in the brain disease region. And at the end is linked to polysolvate 80. Polysorbate 80 is known to be a surfactant that helps blending of polymer and lipid. At the same time, polysolvate 80 can interact with the lipoproteins, therefore allowing the brain penetration property. So as you can see from here, when it's loaded onto intravenously, it'll recruit ApoE lipoproteins and it'll surround the particle with the lipoprotein so that it looks like a big chunk of lipoproteins. Then it will bind to the receptor located onto the blood-brain barrier. Once it crosses the blood-brain barrier through receptor-mediated transcytosis, it uses the anti-amyloid beta antibody to guide the particle to the high amyloid beta region, which is likely to be the disease area, so that after it crosses the brain, then it can bind to the disease region to have more therapeutic benefits. So to easily put, these nanoparticles are loaded with the drug, and then once it is in the bloodstream, it will attract some lipoproteins such as cholesterols, and then it will cross the BBB and deliver the drug into the brain like a Trojan horse in this case that allows the entrance into the castle of the brain. This nanoparticle is called BDNF TPN. BDNF stands for the drug BDNF itself. TPN stands for terpolymer nanoparticles. It has a spherical morphology and the size of 110 nanometer with PDI of 0.21, zeta potential of minus 45 millivolt, and encapsulation efficiency of 99%. The reason for high encapsulation efficiency for our case is because we loaded very low amount of BDNF into the nanoparticles. So only 1.4% of portion of the nanoparticle is BDNF. So the majority is the other pharmaceutical components of it, which is why it has a high encapsulation efficiency to maximize the use of BDNF. So when you load this BDNF onto the terpolymer nanoparticle, as you can see here, the protein structure of BDNF is well maintained, similar to free BDNF, as you can see from this black dot compared to the BDNF terpolymer nanoparticles. And then the bioavailability, bioactivity of this BDNF is similar to free BDNF in a primary neurons. So you can see the lengthening of the neurites in this primary neuron, same as the free BDNF as well as BDNF loaded onto the nanoparticle systems. And on here, we show the stability data of this BDNF. The size and zeta potential of BDNF is stable for more than 24 hours when you incubate them at 37 degrees in the PBS. And their size is also maintained even with or without the anti-amyloid beta antibody conjugation. And when you lyophilize them for the longer storage, you can see the size and zeta potential is maintained for a month. However, the more recent work has shown that even after a year, it shows the stable storage of this BDNF TPN, increasing the translational benefits. Importantly, this nanoparticle provides the sustained release of BDNF from the system. You can see from here that the BDNF is released through the media for more than 60 hours, meaning that there is a sustained release profile of this nanoparticle, allowing the high bioavailability considering a very short half-life. So since it has very short half-life, sustained release of this BDNF would be extremely important for increasing the pharmacokinetic absorption of it. And as you can see here, when you incubate with the primary neuron, the BDNF nanoparticle is uptaken within the cytoplasmic area, but not on the nuclei. And then when you inject them intravenously onto the AD mouse model, you can see a nice uptake to the brain within 15 minutes and signal generally increased and maintained over 1 hour. And then this FITC shows the nanoparticle labeling, and Cy3 shows the BDNF signaling. And you can see that nanoparticle BDNF can increase the uptake of BDNF as well as nanoparticle onto the cortex and hippocampus, which is important for the cognitive function as well as the other entire brain region. So we have tested the BDNF TPN nanoparticle safety. First of all, we performed the immunotoxicity. So we injected these nanoparticles, and after 2 weeks, we checked the immune cell population in this animal model. And you can see that the free BDNF, of course, and BDNF TPN did not show significant changes in immune cell population, suggesting that they are very safe in a therapeutic model. As well, there is a mouse model body weight data suggesting that it is very tolerable, as well as the major organ histological data in heart, liver, spleen, lung, kidney, and brain, and they have shown the safety of this nanoparticle system. While some portion of it goes to the brain, the major organ of uptake is known to be kidney and liver, suggesting they might be the major clearance organ as well. So to check the therapeutic benefits of this BDNF TPN, we injected this nanoparticle or the free form into a moderate stage of Alzheimer's disease mouse. We used TGCR ND8 mouse, which is showing disease progression in a very short time. So at 3 months, it's showing mild stage of disease. At 6 months, it's moderate stage, and 9 months of very aggressive form of AD, which is much faster than the other disease model. After the treatment, we collected the brain for the immunohistological staining. BDNF is known to induce multiple therapeutic signalings. It primarily signals through TRKB receptor, and then it activates AKT, which is known to increase the cell survival, as well as differentiation and neurogenesis. Also, TRKB can activate CAMK, which can induce neuroplasticity. Also, BDNF is known to have immunomodulative function by reducing the pro-inflammatory cytokines. First of all, we check the direct signaling pathway of this BDNF. So after treating either free BDNF or free BDNF TPN or dextrose vehicle control, we found that phosphorylation of AKT is significantly increased with this nanoparticle treatment in both cortex and hippocampus. Also, PCREP activation is checked with this nanoparticle. However, although there is a slight trend of increase in this activation, we could not see a significant change in our system. On the right hand, you can see caspase-3, which is apoptotic signaling, and we can see that the nanoparticle treatment of BDNF TPN allows the reduction of caspase-3 signaling, suggesting BDNF played important role in blocking the apoptosis of the neuronal population. Also, NEUN, which is a neuronal marker, is increased with these BDNF TPN nanoparticles, however, not with the free BDNF system. So BDNF TPN also plays important role in immune modulation. IBA1 and GFAP, which is a microglia and astrocyte activation marker, has been investigated with this nanoparticle system. You can see that while free BDNF shows slight reduction in its activation, significant benefit could be only found in BDNF TPN nanoparticle system in both microglia and astrocytes. On here is a synaptophysin and GAP43, which shows the synaptic marker in this AD brain. The BDNF particle was able to increase the synaptophysin and GAP43, suggesting it has a synaptic benefit with this nanoparticle treatment. So together, it is known to reduce the inflammation and increase the synaptic function as well as neuronal survival, therefore allowing the therapeutic benefits of the Alzheimer's disease. So based on this positive finding, we have performed the behavior study. So this is called fear conditioning test, where on the day 1, the mouse received the electric shock with the sound located on the certain box. And then if the mouse has a good memory, it will remember the box, the location of this mouse, as well as the cue, which is the sound that came with the electrical shock. So that's how they test this behavior of this AD mouse model. On day 2, you locate the same mouse in the same box that it received the shock without any shock and see if it remembers the contextual memory. As you can see from here, the vehicle control mouse did not remember much about this contextual memory. However, the free BDNF seems to have a slight increase in this BDNF, in this box contextual memory. And however, BDNF TPN showed much better cognitive improvement in this contextual memory, suggesting that TPN nanoparticle system can increase the benefit of this BDNF therapy. On the last day, we performed the cue test, where the mouse is located onto a different box, and then the sound that it received with the electrical shock on day 1 is given to this animal to see if they remember the sound that came with the shock. On this one, you don't see much change in this cued memory, likely because the contextual memory is related to hippocampal function. However, cued memory is related to amygdala, which is more related to the fear. Therefore, the BDNF TPN nanoparticle is more beneficial for the improvement of hippocampal function, but not on the amygdala. So in conclusion, this polymer lipid nanoparticle system allows the efficient delivery of BDNF into the brain as well as the disease area. So when you give this brain-penetrating BDNF polymer lipid nanoparticle into the tail intravenous vein, it'll go to the brain and target the disease region with the anti-amyloid beta antibody. Therefore, it can reduce the apoptosis of the neuronal cells and reduce the activation of microglia and astrocytes, therefore reducing the inflammation within the brain. Furthermore, this BDNF TPN can increase the synaptic plasticity, which is the neuronal communication route. Therefore, it improves the cognitive function. So the future work of our lab is looking into the other pharmacological aspect of BDNF. For example, we aim to perform the synaptic function assay such as LTP or LTD measurement with this BDNF TPN technology, as well as checking to see if the combination therapy in this BDNF nanoparticle, as well as other other Alzheimer's disease drug, such as antioxidant or amyloid beta antibody therapy, to see if this nanoparticle system can benefit the Alzheimer's disease therapy. So this work was supported by Korean Honor Scholarship, Ontario Graduate Scholarship, and then Pharmaceutical Science Departmental Scholarship, as well as Western Brain Institute and NSERC Instrumental Group. This is our group, and then our lab is shirleywulab.com if you would like to visit for more information about our recent advancement in the drug delivery therapy. Thank you.